All right, so today we're going deep, really deep into quantum computing.
Okay.
We're talking about its history, its origins, all the way to, well, where we are now.
Sounds like fun.
Yeah, I think it'll be really interesting because you've given me some really incredible material to dig through.
Yeah. It always amazes me how two completely different fields, like quantum mechanics and computer science,
Right.
somehow just slammed together to create this whole new world of technology.
It's wild, and our source material even points out how for so many years they were just totally separate, right?
Totally.
Like you had quantum mechanics trying to figure out all the weirdness of the subatomic world starting back in the 20s.
Yeah.
And then you have computer science, still in its baby steps in the 40s,
Right.
just trying to build these number-crunching machines.
Mhm.
And yet both of them, completely separately, were already super important during World War II.
Yeah. Well, computers were crucial for code breaking.
Oh, yeah, cracking those enemy codes.
Absolutely. And meanwhile, you have quantum physics powering the Manhattan Project.
Right, the atom bomb.
Yeah. So it's pretty amazing how both of these fields were already having this huge real-world impact back then, even before they converged.
It's like a perfect example of how things that seem totally theoretical can suddenly become super practical and even, world-changing.
Mm-hmm.
So how did these two fields actually start coming together? How do we go from separate but impactful to suddenly this new field of quantum computing?
Well, I guess it all started when physicists started running into roadblocks.
Okay, what kind of roadblocks?
Well, as digital computers got faster and faster, physicists found it harder and harder to simulate complex quantum systems.
Because they're so complex.
Exactly. It was like trying to fit an ocean into a teacup.
Yeah, I can see that.
The old tools just weren't cutting it anymore.
Right.
They needed a totally new approach.
So this is where the quantum part comes in.
Yeah. It was crazy in the early 80s. Yuri Manin and Richard Feynman, they both independently came up with this radical idea.
Okay, let's hear it.
Why not build computers that actually use quantum mechanics?
Instead of trying to simulate it.
Exactly. Harness the weirdness of quantum mechanics to actually do the computing itself.
That's so cool.
Right. And around the same time, Bennett and Broussard, they came up with quantum key distribution.
Okay, what is that?
It's basically a way to use quantum mechanics to share encryption keys.
Like for keeping messages secret.
Yeah, and it's virtually unbreakable. Seriously. So you can see how these early ideas really started to move quantum mechanics out of the labs and into the real world.
And this is where we start talking about quantum algorithms, right? You got it.
Sure.
Back in the 80s and 90s, you had algorithms like Deutsch's algorithm, Bernstein-Vazirani, Simon's algorithm.
And what did they do? I gotta confess, algorithm is already a word that makes my head spin a little.
Well, they didn't really solve any practical problems at that point.
Oh, okay.
But they were super important because they mathematically proved that quantum computers could do things that classical computers just couldn't.
Well, one big thing is this concept called quantum parallelism.
Okay, break that down for me.
So think about it. A normal computer, it processes information bit by bit, one after the other, right?
Yep.
But a quantum computer, because of superposition.
Superposition.
Right. It means a qubit can be in multiple states at the same time.
Oh, wow.
So it can process a ton of information all at once in parallel, which is just mind-blowing.
Yeah, that is mind-blowing. But back then, was anyone really sure if building a quantum computer was even possible?
Well, that's the crazy thing about science, right?
Figure.
It's a leap of faith.
You just have to try it out.
Exactly. And then in 1994, Peter Shor, he drops this bombshell algorithm.
Okay, I'm on the edge of my seat. What did it do?
It showed that if you had a powerful enough quantum computer, you could break RSA encryption.
Isn't that what we use for, like, everything online?
Pretty much. And Diffie-Hellman encryption, too. Those are the big ones for secure communication online.
So this algorithm basically said, hey, quantum computers could totally upend cybersecurity as we know it.
Bingo! And that's when things got really serious.
I bet. Governments must have been freaking out.
You know it. Suddenly, quantum computing was a matter of national security and everyone was pouring money into research.
That makes sense. So what happened next?
Well, the discoveries just kept coming. You had Grover's algorithm in 1996.
Okay, what does that one do?
Basically, it made searching through unsorted data way faster.
Like finding a needle in a haystack?
Yeah, but imagine a haystack the size of the planet.
Yikes.
And then Seth Lloyd, He proved that quantum computers could simulate any quantum system.
Didn't we talk about that earlier with Feynman?
Exactly.
Oh.
Lloyd proved that Feynman's idea was actually possible.
So this was like a chain reaction of amazing discoveries.
It really was.
But how do we go from all these algorithms to actually building a quantum computer?
Well, it was a long, slow process.
I bet.
Scientists started by building tiny quantum computers, like with just a few qubits.
A few? Like how many?
Well, in 1998, they built one with just 2 qubits.
2. That doesn't seem like a lot compared to the billions of transistors in my phone.
I know, right? But it was a huge step because it proved that it could be done.
Okay, I get it.
So from there, the focus shifted to making more qubits and making them more stable because they're really fragile.
So is this the race to what they call quantum supremacy?
Yeah, that's basically the goal, to build a quantum computer that can do something faster than any classical computer on Earth.
Like a supercomputer.
Exactly.
And our source material mentions that Google made some pretty big claims about that in 2019, right?
They did. Google and NASA, they said they achieved quantum supremacy with their Sycamore processor.
That's the one with 54 qubits, right?
Yep. They did this calculation that would have taken a classical supercomputer thousands of years.
Wow, that's amazing.
But of course, it was super controversial.
Really? Why?
Well, some people said the calculation they did wasn't really practically useful.
So kind of a made-up problem.
Kind of, yeah.
And some people even question whether it really was supremacy at all.
Right, so it's still a really debated topic.
I can see why. It's all so complex.
Exactly.
Well, it's clear that quantum computing has come a long way from those early theoretical ideas, from code breaking to this supremacy debate. It's all so fascinating.
Yeah, and the craziest part is that we're really just getting started.
What do you mean?
We've only scratched the surface of what quantum computers might be able to do.
Give me some examples.
Well, think about it. Breaking encryption is just one thing.
Right.
But what about designing life-saving drugs, or creating brand new materials, or solving climate change?
Whoa.
The possibilities are almost endless. It's just a matter of time and figuring out how to harness this incredible power.
So the next chapter of quantum computing is basically a giant question mark.
It is, and it's up to us to figure out what that future will look like.
And that brings us to the end of our deep dive today.
Wow, time flies when you're talking about quantum mechanics.
It really does. I hope everyone listening enjoyed this journey through the history of quantum computing.
Me too.
And we'd love to hear your thoughts. What do you think the future holds for quantum computing? Head over to our website and let us know.
Yeah, join the conversation.
Until next time, keep exploring the quantum world.
See ya.